Hello everyone, my name is Jiahao from UCLA HCI Research. Today I want to talk with you about the paper Robiot, a design tool for actuating everyday objects with automatically generated 3D printable mechanisms. I worked on this project with Jeeun from CSE department at Texas A&M University and Chen from HCI Research at UCLA. Let's first see an example. Here I am doing some soldering work, and I can't see the object clearly. There's a reading lens on the desk lamp, and I want to look through it. Therefore, I can look at the object more clearly. But both of my hands are occupied by the soldering work. I ask myself, how can I lower the lamp without using my hands? Wouldn't it be better if this lamp is part of the IoT of my home and I can use my voice to control it? That would pretty much solve my problem here. Before I discuss that in details, I'd like to zoom out for a little bit. The Internet of Things is getting increasingly ubiquitous and start to support more and more physical tasks. For example, an auto faucet can enable users to turn on the faucet without using their dirty hands. And an auto window can be opened or closed automatically. And Guy Hoffman's robotic lamp paints a larger picture that in the future, what IoT would be like. Everything can become robotic and part of the IoT. He's looking for his rubber. So it is important to enable end users to design such kind of robotic behaviors. But when it comes to robotic design, things can get overwhelming for end users because they lack the expertise in this kind of area. So we ask ourselves, can we provide a tool that helps novice end users to design such kind of robotic behaviors? RetroFab and Reprise and Encore focus on design tool for non-expert users to design functional parts of 3D objects. But when designing robotic behaviors, we need to answer two specific questions. First is, can we enable users to naturally express how they want an everyday object to behave robotically? And can we extract mechanically meaningful information from such user expression? Therefore, we introduced Robiot, a design tool for actuating everyday objects with automatically generated 3D printable mechanisms. Let's go back to the example in the beginning. With Robiot, a novice user can design and fabricate some mechanical mechanisms like the white parts in the video, and they can remotely control the angle of the lamp by only saying down. Down. So in this talk, I will discuss Robiot in 4 different parts: user walkthrough, example applications, technical details, and user study. When using Robiot, all a user has to do is just to record a short video demonstrating how he manipulates one typical objects. And then he uploads the video to Robiot software and adjusts the design parameters, such as the size or the type of the mechanisms. And then Robiot will generate the 3D model of the mechanisms and will send it to the printer to print it out. The user can come to collect the printed part the next day and install them by himself. And finally, he can interact with the object. Let's see more examples showing how user could use Robiot to interact with other everyday objects. The user can use Robiot to upgrade a desk lamp, which is previously shown, to remotely control the angle of the lamp. Our project mainly focused on the fabrication of the mechanisms, and we use some outside microphone or existing sensors to enable the interaction. Done. And a busy office worker can use Robiot to design some mechanisms for the spray bottle that it can water the desk plant according to a predefined schedule. And the user can also design some mechanism for this drawer, and it can open automatically while the user is holding a lot of groceries. Drawer, open. So these examples are all designed by our participants during the design session, and here are more examples. A user can use Robiot to upgrade a faucet to an auto faucet, and can upgrade a squeeze bottle to an auto squeeze bottle to squeeze out the dish soap automatically. And the user can also design some mechanisms as simple as a stapler. So by now, you must be really curious that how does Robiot design such kind of mechanisms by only analyzing a simple short video? So remember the question we need to answer to provide a tool for the users? The answer for the second question is that Robiot needs to extract two major information from the user input video, which is the first, the type of joint that is manipulated, and the second is, on this object, which part is the ground and which part is maneuverable. Before I discuss these two, explain these two in details, let's review some mechanical design knowledge first. The motion of most real-world objects can be represented by a rigid body motion, which means the object can be decomposed to links and joints. For these complicated humanoid robots, the body parts can be represented as links and joints. For example, the arms are moving around the elbow, which makes the arms the links and makes the elbow the joint. And for each joint, it can be either classified as a revolute joint, which means the link is moving in rotary motion, or a prismatic joint, which means the link is moving in linear motion. Let's take the lamp as an example. These two parts is the link, and the pivot is the joint. And since the link is moving in rotary motion around the joint, so it is a revolute joint. A Robiot provides a library of different mechanisms to make it suitable for different type of joints and different space condition. From top down is 4-bar linkage, pin slot, and gear rack. And after knowing the type of joint, the rationale to choose the best mechanisms is that Robiot needs to know on this object which part is moving and which part is still and so-called ground to get the dimension information of this object. Also take the lamp as an example. The upper arm is moving, which makes it a maneuverable part, and the lower part doesn't move, which makes it a ground. So what Robiot does is video analysis plus geometry processing. Robiot will first maintain a repository of object 3D model as a pre-processing step. And then, after the user input the video, Robiot will first do a foreground extraction to extract the object from the video. And then, Robiot will do a video-based motion pattern analysis to determine the type of joint by using optical flow to track all the feature points on this object. After that, Robiot will fit an arc to the trajectory of each feature point, and according to the distribution of each fitted radius, it can be either classified as a revolute joint or a prismatic joint. The rationale beneath it is that the fitted radius of a revolute joint is relatively small, while the radius of a prismatic joint is close to infinity. Let's take, for example, for this lamp, the fitted radius is similar to the second arm of the lamp, which makes it the revolute joint. And for this drawer, the fitted center of the arc is far away from the center of this figure, which makes the radius close to infinity, and which makes it the prismatic joint. Now we know the type of joint. The next step is to find the ground and the maneuverable parts on this object. The Robiot will first classify all the points on the object as either a moving point or a still point. And at the meantime, Robiot will take the extracted object as a snapshot to match the corresponding 3D model in Robiot repository. And after that, Robiot can do a segmentation by unprojecting the 2D data onto the 3D model to get the maneuverable and ground parts on this object. And after that, Robiot can generate different actuation mechanisms for this object and also the installation guideline for the users. We also conducted a user study in which 6 users go through the whole design process of using Robiot and finally interacts with the objects that they designed. So these are the results all designed by our participants, which is great. And during the evaluation session, the participants value the easiness and usefulness of using Robiot. And please refer to our paper for more detailed information. But some limitations are also reported by the participants. For example, some reported that when they are picking one typical mechanisms, they don't know how things work. So in the future work, we will enable users to explore a larger design space of different results to feel more engaged in the design process and with less confusion. Some also thinks that the mechanisms outside of the objects looks strange or bulky. So we will explore new mechanism design to improve the form factor. And now Robiot only allows design 1 degree of freedom at a time. And in the future, we will try to enable more complicated actuation, such as the multiple degree of freedoms. So in conclusion, Robiot is an end-to-end pipeline that requires very minimal user input to automatically generate 3D printable actuation mechanisms. And extracting mechanically meaningful information from user demonstration can potentially generalize to other manufacturing techniques. That's my presentation. And at the meantime, I'm eagerly looking for an interposition during next summer in the area of design tool or digital fabrication. If there is any opportunity, please let me know. Thanks. I'm happy to take any questions.
Hi, thanks for the talk. So, how did you take care of tolerances and how did you ensure that the 3D printed part actually fits onto the object? Because you can have different...
sorry, can you repeat that again? Sorry.
The tolerancing, how did you take care of the tolerancing of the 3D printed part so that the printed part can be fitted onto the object?
You mean for the fastener?
Yeah, like... so in the lamp, you are fitting the 3D printed part onto the lamp, right?
Mm-hmm.
So the fitting has to be like pretty secure, right? So and while you're 3D printing an object, usually you have to iterate a couple of times until you find out the correct tolerancing for fitting?
We design a clamp mechanism or a glue to fit the mechanism onto the object. Or if you are saying how do we decide find the size of the fastener, we have the 3D model of it, so we can have the shape and the size information. I hope this answers your question.
Yeah. Okay. Thank you.
Thank you.
This was definitely an interesting talk that I haven't thought of objects in this way. But I was wondering, because you're turning regular objects into mechanical and electronically dependent materials, does it inhibit the function of the regular device in any way?
I think so.
Hi, really nice talk. I wanted to ask about how did you project a 2D image over a 3D model, because I believe the projection, the current plane would really matter when projecting the 2D image over the 3D model, because it would really matter how you're looking at the 3D model when you're projecting it. So how do you find the best projection?
For projection, because when I mentioned we use the extracted object to match the corresponding 3D models, so we will also to get the right angle view of this 3D model, which means if the user record a video that is vertical to the object, so we will try to find the angle of the view of this object in the 3D model. Okay. So therefore, we can implement a basic projection and projection to the 3D model. Thank you.
Great, thanks.
Awesome. Thank you very much for your question.